Okay, so question 8 is a probability question. The first one's about dice. Two fair dice, six-sided, so no Dungeons and Dragons stuff. And you roll them and add them, much like in backgammon. And it's worked out with this argument that the probability of getting a 12 is an 11th. Now, without calculating the actual probability, we've got to explain why it's wrong, and whether the actual probability should be less than or more than an 11th. Okay, so let's look at the argument. The smallest score is 2. Is correct. The highest is 12, is again correct, and 11 possible scores. Those are all correct. But not all scores are equally likely. Okay, for example, a 2 can be a 1 and a 1. A 3 can be a 1 and a 2, or a 2 and a 1, etc. Okay, so if you know this problem as you go through, you get more and more, and actually 7 is the luckiest number. But this should be enough to show that the probabilities will be different as different number of ways to score results. Not my finest English, but hopefully that makes sense. Okay, a 12, for example, again, you can only get with a 6 and a 6. An 11 you can get with a 5 and a 6, or a 6 and a 5. Okay, so the next part is whether the actual probability should be less than or more than an 11th. Now, less than, because if you think about all the probabilities added up, we're going to say some are going to be more likely than others. So you're almost going to get this sort of shape. 2 and 12. Okay, so what's happening is, if they were all just as likely as each other, they would all be 1/11th. It would be evenly spread. But as we look at it, 2 is much less likely than 7, and you kind of need to compensate. So that will be as, well, maybe it won't, it'll be, these will sort of they all need to add up to 1 in total. Right, part B, mustard seed on a whole load of circles. Okay, these are the sorts of problems I think it's quite easy to start sort of panicking about, because it tells you, for a start, it tells you give us the 3 significant figures, but there don't seem to be any figures in it. And then you can sort of think, well, it doesn't give me the whole carpet. So what we can do is just start off with the most basic example. Okay, we've basically got a whole load of these sorts of shapes. and I'm going to say that's a circle with a radius r. And essentially, it doesn't really matter. We're going to assume that what we're trying to find out is the probability, given that sort of shape, of the seed landing in the white section. So it's going to be the probability of it landing here, 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 or here, which is, we can write as the probability of it landing in the white section is the area of the white section divided by the total, or out of the total area. Okay? Now, the total area, so we've got r here is 2r squared. We've got just a square here, 2r, which is 4r squared. Get this back. Oh, I'm going off camera again. I don't do this in a classroom, otherwise I'd be writing all over the walls. Anyway, the area now we need to find the white, and the white we can do, well, if we work out the shaded area, the black area, and subtract it from the total. So the white area is this total area minus this area, and this is a circle, so it's pi r squared. Okay, we still don't know what r is, but we can say even if it was 1, we can multiply it, and the proportions and the likelihood should stay the same. So our probability, again going back to here, the probability of white is the white area, which is 4r squared minus pi r squared divided by 4r squared, the total area. And you can have a common factor here, which is 4 minus pi over 4. Give your answer to 3 significant figures. Okay, let's go calculator. Okay, I make that 0.21523. There's your probability.